Imagine a skyscraper whose windows are as clear as crystal yet stronger than steel, or spacecraft windows that shrug off micrometeorite strikes, and smartphones so durable their screens could last decades without a crack. This isn't just fantasy. The material once thought to exist only in Star Trek has stepped out of fiction and into the lab. Transparent aluminum is real, and it's poised to change how humanity builds everything from cars and homes to satellites and submarines. And this is not just about replacing glass, it's about reshaping the way civilization interacts with the physical world itself. Think about the psychological shift this could bring. Humans living in cities where transparency and protection coexist, where fragility gives way to resilience without losing beauty. Imagine the cultural impact of skylines transformed by structures that look delicate yet are nearly unbreakable, shifting how we define safety, design, and even aesthetics. The story begins with a deceptively simple question. Can something be both transparent like glass and as hard as metal? Ordinary glass fractures under a sharp strike. A child's baseball can shatter a window with just 20 joules of force. Compare that to a bullet-resistant sheet of transparent aluminum ceramic, which can withstand forces exceeding 1,200 joules. That's about 60 times tougher while remaining crystal clear. For perspective, the human skull fractures at around 70 joules. This means a pane of transparent aluminum could stop a blow that would shatter bone many times over, and still let the light shine through. Now imagine what this means for cities, for vehicles, for safety, and every environment where glass is used today. A classroom could have walls of light yet be safer than concrete. A car accident could play out with fewer shattered shards, lowering injury rates dramatically. Hospitals could build transparent partitions that resist impacts while creating calming, light-filled spaces for recovery. This material, technically known as aluminum oxynitride or ALON, behaves like a window from the future. To the naked eye it looks like ordinary glass, but at the molecular level its atoms are locked into a crystalline fortress. Glass is amorphous. Its atoms are disordered like frozen liquid, while ALON is crystalline, like a gemstone. That gives it a unique ability to resist stress and disperse impact energy instead of fracturing. It's not indestructible, but it's close enough that militaries are already using it for armored vehicles, aircraft sensors, and even missile domes. In battlefield conditions where clarity and protection are both mission-critical, ALON outperforms anything traditional glass or plastics can offer. A pilot flying at Mach 2 needs a canopy that won't fail under bird strikes or debris. ALON answers that demand with strength and visibility. Submarines could peer through deep ocean pressures with portholes of transparent armor that shrug off crushing forces. Pause for a moment. What would life look like if this technology scaled to everyday use? Picture cars with windows that never crack, eliminating the $20 billion global cost of windshield replacements every year. Imagine smartphones with transparent aluminum screens that resist scratches from sand, keys, even knives, cutting down on the 200 million replacement screens sold annually. And visualize a world where buildings can be both open to light and resilient against storms, earthquakes, or even explosions. In hurricane zones, transparent aluminum could replace storm shutters entirely, letting in sunlight while protecting families from wind and debris. In earthquake-prone regions, panes could hold together where glass would otherwise shatter, reducing injuries from falling shards. In schools, protective barriers could shield students from danger without creating dark, oppressive spaces. Prisons could use transparent aluminum walls to balance visibility and safety, reducing blind spots while preventing escape. This is not just stronger glass, it's a potential rewrite of the built environment. If this excites you as much as it excites us, make sure you don't miss what's coming next. Subscribe, like, and turn on notifications to stay ahead of the curve as we uncover the future of materials science. The real magic lies in the numbers. Ordinary soda-lime glass, the kind used in most windows, has a hardness of about 5 on the Mohs scale. Quartz crystal sits at 7. ALON reaches above 8.5, placing it in the league of sapphires. Yet unlike sapphire, which is expensive to grow in large sheets, ALON can be manufactured in blocks and then polished to optical clarity. That's the game changer: scalability. A mini Fermi estimate shows that if even 10% of the $100 billion global glass market switched to transparent aluminum within a decade, that's a $10 billion annual industry emerging from what used to be science fiction. And that doesn't account for secondary effects: reduced insurance claims, lower maintenance costs, and improved energy efficiency from stronger, thinner windows. Multiply that across millions of buildings, And we're talking about energy savings in the hundreds of terawatt hours annually. That's equivalent to powering entire nations just from better windows. And when you extend those savings globally, transparent aluminum could realistically offset as much CO2 as entire mid-sized nations emit. But transparent aluminum is only the beginning. Exotic alloys are rewriting the rules of what metals can do. Shape memory alloys that remember their form can twist and bend but return to their original state with a pulse of heat. High-entropy alloys mix 5 or more elements into stable configurations that traditional metallurgy never imagined, producing steels 2 or 3 times as strong as anything found a century ago. These breakthroughs are not isolated curiosities. They're the building blocks of the next technological age. Without them, future industries from aerospace to clean energy would hit a wall of material limitations. Imagine renewable energy farms where turbine blades never fatigue, pipelines that resist corrosion for centuries, or medical implants that last a lifetime without rejection or wear. Take high-entropy alloys for example. Researchers have found configurations that remain ductile even at -200 degrees Celsius, conditions where ordinary steel would snap like dry spaghetti. This opens doors for deep space exploration, Arctic construction, and cryogenic storage. Or consider magnesium alloys that are 75% lighter than steel yet stronger than aluminum, enabling cars and aircraft that sip less fuel while carrying more. Every kilogram saved in aerospace saves thousands of liters of fuel across a plane's lifetime, which translates directly to lower ticket costs and reduced emissions. A commercial jetliner carrying 200 passengers consumes about 3 liters of fuel per passenger per 100 kilometers. Shaving even 5% of that through lighter alloys would save airlines billions while cutting global emissions by millions of tons. Extend that logic. Cargo ships built with advanced alloys could slash their 2.5% share of global CO2 emissions, changing the equation for climate change. In other words, these alloys don't just bend physics, they bend economics and sustainability in our favor. Extend further. Satellites built lighter could carry more sensors, giving us sharper climate data and better disaster predictions. The open question is, how fast will this transition happen? Materials adoption often takes decades. Steel took nearly 50 years to overtake iron in construction. Plastics reshaped consumer goods over a similar timescale, but digital simulation and nanostructuring accelerate the process. A component that once required 100 prototypes can now be modeled with millions of virtual tests before a single block of material is even cast. That speed-up could cut development cycles by an order of magnitude, making futuristic alloys mainstream within 10-15 years instead of half a century. Consider how quickly lithium-ion batteries went from lab experiments to powering nearly every smartphone and electric car, a matter of 2 decades. Materials innovation is entering its own exponential curve, and unlike energy storage or computing, new materials ripple across every industry simultaneously, multiplying their effects. That multiplier effect could dwarf even the digital revolution when combined with AI and automation. And the stakes are enormous. Imagine the defense implications. Lighter tanks that resist more damage, aircraft canopies that withstand supersonic debris, even helmets that protect soldiers against blasts while letting them see clearly. Imagine the consumer implications. Cars with scratch-proof paint, homes with storm-proof windows, wearables that don't corrode with sweat or salt water. Even space habitats orbiting the Earth or sitting on Mars could benefit from walls of transparent aluminum, letting colonists look out into the void without fear of impact damage. One can picture a Martian greenhouse where transparent aluminum panels let in precious sunlight while holding out deadly radiation and micrometeoroids. Lunar bases could feature domes of transparent alloys that allow settlers to stargaze while being shielded from the harsh vacuum. Every aspect of modern life touches materials, which means every breakthrough here ripples through the global economy. Researchers are even experimenting with alloys that self-heal, like living tissue. A microscopic crack forms, atoms migrate, and the gap literally fills itself. If perfected, this could extend the life of engines, bridges, or spacecraft hulls from decades to centuries. The implications border on the mythic, a civilization that builds once and benefits for generations. Self-healing materials hint at infrastructure that never collapses, machines that never truly wear out, and spacecraft that can endure decades of interstellar travel. Combine that with transparent aluminum and you could envision orbital colonies with walls that never weaken, a permanent human presence protected by smart materials. It points toward an economy where maintenance becomes less about replacement and more about monitoring. A future where cities heal themselves like living organisms. And this is only the beginning. Transparent aluminum and exotic alloys are stepping stones towards something even more profound. Programmable matter, where atomic-scale engineering lets us dial in properties on demand. Glass that darkens with sunlight yet is harder than diamond. Metals that flex like rubber but bear loads like steel. Concrete that repairs itself overnight. Fabrics that adjust their thermal properties in real time. Materials science is the quiet revolution, but it underpins everything else. AI, quantum computing, aerospace, medicine. Without stronger, lighter, smarter materials, those visions remain fragile. With them, the future becomes not just possible but inevitable. Imagine prosthetics that feel alive, skyscrapers that respond to wind like living trees, or vehicles that adapt their skin to the environment. This is not science fiction anymore, it's the horizon. If the idea of windows that can stop bullets or bridges that heal themselves makes you wonder what's coming next, you're not alone. This is the kind of future that feels like it belongs in science fiction until it suddenly doesn't. And when that moment arrives, you'll want to be the first to understand it. The breakthroughs ahead could redefine not only technology but the way humans interact with the physical world itself. The materials revolution may be the single most transformative shift of this century, hidden in plain sight, waiting to erupt. And the question that lingers is, will we be ready to harness it? Will we build responsibly, or will we repeat the mistakes of past industrial ages? The answer will shape the next 100 years. The most transformative stories are unfolding right now, and you'll want to witness them as they happen. Subscribe, like, and turn on notifications. This is Tech Mythos.